The broadcast is now starting. All attendees are in listen-only mode.
All right, we're just going to give it one more minute here to see if we get any more attendees before we begin. For those that just joined, we're just giving it a little bit more time here, maybe 30 more seconds before we begin. Okay, I think we'll go ahead and get started. Thank you. Welcome, everyone. This is the Department of Energy Better Buildings Space Conditioning Tech Team. Today, we're going to be talking about thermal energy storage and opportunities surrounding the technology. My name is Miles Hayes. In the room, we've got Michael DeRue and Carl Hein. And then on the phone as well, we have a guest speaker, Mark McCracken with Train. Start off, I just want to discuss a couple space conditioning tech team updates, recent publications that are available, SMC technical report, DWT technical report, cooling tower water treatment technologies. Michael, if you want to speak to any of those.
Just that SMC technical report is a high efficiency smart motor, and the application was in a refrigeration condenser fans. And then Dynamic Water Technologies report is a cooling tower water treatment, chemical-free cooling tower water treatment technology that we completed that testing recently. And then there's several other cooling tower water treatment technologies that were tested along with the GSA, and we have those reports available as well.
Great. Another update, we're ramping down this year with the Advanced Rooftop Unit campaign. Sent out a survey asking for feedback. And we've also got some upcoming HVAC resource map updates as well. If you want to go ahead and pass control over to Mark.
Okay. Well, thank you, Miles. I appreciate the opportunity to speak to this group. How's that? Can you see the screen?
Yep, we got it.
All right, great. It's a pleasure being able to speak to people on a topic I've been involved with for over 40 years, as energy storage is going to be huge for the future and a low carbon future, and we're going to talk about how it applies going forward. I always like to start off with describing what is on the left, which are really forms of fossil fuels. And fossil fuels are stored energy. They're not just energy, so that's a unique characteristic. And yet we're trying to replace it with renewables, which is just the pure energy. So the question becomes, where is the storage gonna come from? And where the storage is not now is on the grid. The electric grid right now has essentially no storage on it. It's a one-way device pretty much. The power flows in one direction. Money flows the other direction, but it's all instantaneous. So the power you're using right now is being generated at this same second. In the future, as we move forward, a lot of energy storage is going to have to be added to the grid as we add different sources of renewable, the wind in areas of Texas. There's so much wind that they have to curtail at night. It's happening with PV. Because we don't have energy storage to suck the energy up to use it and make it dispatchable later on. So energy storage is going to be added to both sides of the electric meter in very large amounts to replace the characteristic of the fossil fuel that it's replacing. I like to give an example of a net zero or a zero energy building and look at it in the respect with storage. So a zero energy building, or what we normally talk about is that a net zero building will have, wind turbines on it or solar panels or something to collect that energy. And I guarantee you it'll have a lot of energy storage on it. It'll have electrical batteries, it'll have thermal storage, which we're starting to call thermal batteries, and it'll have fossil fuel in the ground because it's going to have backup for that in case you don't have the first two or your renewable resources for a week or two. So lots of energy storage is going to be at the site of an off-grid building, okay? It's going to be mandatory. Well, just because you connect a couple wires to that building and connect it to the grid, those storage issues don't just magically disappear. They really just get outsourced to the grid. And right now, that's all being backed up with fossil fuels or nuclear. And so it's, a net zero building, if you think about it from a grid's perspective right now, is about the worst possible building you can put on the grid. It doesn't use any net power from the grid for the year, but the grid is giving it this amazing services, as much power as you need anytime you need it. And really that's the storage aspect of the grid, yet the grid doesn't have any storage, so it's all instantaneous. So that's gonna have to change. So if we look at the different types of energy storage out there, I kind of break it up into two different sides of the electric meter. So you've got the grid side, and there's pumped hydro, compressed air, flywheels, and supercapacitors. I'll be talking about those in a minute. And then on the building side, you're really going to only have two major types. You're going to have chemical batteries, and then you're going to have thermal mass, which would be passive, or thermal batteries, which are more of an active system. So let's kind of look at the different types of storage that are out there. So on the grid side, you've got pumped hydro. Most people on the call probably know what pumped hydro is. If you don't, basically you take water, you take a big pump and you pump water up a mountain and you make a lake. And then during the daytime, you empty the water. It goes through the pump the other direction, and now it makes a pump into a generator. And you take that power and you get that energy back. So the major issue with pumped hydro is it's only about 70% cycle efficiency. So you put a megawatt hour of electricity into it, you only get about 0.7 megawatt hours back. So that's an issue, but there is pumped hydro out there. It's probably the largest form of energy storage that is on the grid. There is some on the grid right now. It's less than 1%, but pumped hydro is a major portion of that. Electric batteries, everybody knows about lithium-ion batteries are coming on. There's all sorts of different types of battery chemistries out there, and we're now starting to see them added to the grid. They're usually going in areas that are constrained. There are major goals in California for getting storage on the grid, and a lot of the utilities are putting in electric batteries on the grid side of the meter now for we'll call it experimental and really very functional systems now. There's compressed air storage. So compressed air is you have a big cavern, maybe a salt cavern underneath the ground. You pressurize it up with energy that you collect, and you pressurize the gas. You can then bring that air back up during the day, and it can either go into a combustion turbine engine, so you don't have to be compressing the air. It's already compressed, so it makes it very efficient, or it can run a turbine directly, so it's another way to store it. And then finally, flywheels. Pretty much everybody, physics, about, potential energy, so that's the pumped hydro. Well, this is the kinetic energy storage, so you have large masses that get spinning at very, very high RPMs, and you can take that that energy back. So these different technologies are good for different things. For instance, flywheels and batteries are very good for power quality on the grid, so that's keeping 60 cycles 60, where pumped hydro is more of energy management. So you can pump up a lake and you can wait weeks if you want before you take the energy back. So it's a longer time period. So let's look at the buildings. When you get to the buildings, now you've got batteries. You've got electrical batteries for doing the electrical loads, and thermal. The thermal can be either chilled water, hot water, or it can be ice in tanks. So those are the two major technologies that you have there now. A Bloomberg report just showed that in the future, they're seeing, we'll call it 50-50 split for energy storage behind the meter and in front of the meter. So on the grid side or the building side. So there's going to be massive amounts of energy storage that's going to be added, and it's going to be split between building side and grid side. I like to give the example of thermal storage. You know, everybody on the call, I assume, would think it's a bad idea to start making the ice cubes for a party when people start walking in the door. And so if you just take this, you know, minor example of thermal storage, it turns out you need about a pound of ice per person coming to your barbecue. So you got 20 people come in, you know, you need maybe 20 pounds of ice that you buy at the store the day before. You make it for a couple of days in your refrigerator. Well, I like to ask people, well, how much energy, let's talk about pounds of ice, would you need to cool that same person when they go to their office the next day? And it's an easy calculation. The architects on the phone would know that there's about 100 to 200 square feet for each person in a building. And the engineers on the call will know that 300 square feet can be air conditioned by a ton of air conditioning. That's not a very efficient building. A more efficient building is 400 square feet with a ton, and 500 square feet is a pretty efficient building. So I took the one in the middle, and then for 8 to 10 hours, it turns out it's 160 to 400 pounds of ice per person per day to keep them cool in their office. So if it's ludicrous to make, you know, to try to start making 1 pound for people coming to your party, why isn't it hundreds of times more ludicrous for buildings to act like they didn't know you were coming and turn on huge chillers or equipment in the basement, draw all this power in order to meet this load? So energy storage makes sense in buildings, and the way we've been doing it has caused lots of problems on the grid. This is a utility load factor for the grid. Load factor is the average load divided by the peak load. So you can see in the 1960, we'll call it, we were closing on a 70% load factor. So that's 70% of the entire hours of the year. We were averaging about 70% of our utilization of our overall capacity, which is pretty high. Right now, we're below 50% utilization. So what does that mean, really? Well, if you take the reciprocal of the 50%, we have twice as much generation, transmission, and distribution as we need in this country right now to supply our buildings if we used electricity at a level rate day and night, but we don't. So what this chart means is, yeah, our growth in energy usage of electricity has gone up a lot since the 50s, but our on-peak usage has gone up much faster than the off-peak usage. So we're not using the equipment very effectively. If you look at what's called a duration curve is all the hours of the year, so 8760 in the lower right-hand corner there. This is for the New England grid. So the lowest output hour for the New England grid is about 9,000 megawatts. So that's the far right side. On the far left side, the highest output hour is 28,000 megawatts, and you stack it up numerically going in between that. So you can see that the average in the center is about, you know, 50%, 53%, something like that. You also see that the last 20% of demand, or 21% of demand, is used less than 2% of the hours of the year. So there's a tremendous amount of capacity that's installed for a very short period of utilization. Now it gets worse than that. I was in New England, 40% of the total dollars for installing their grid and running their grid is associated with meeting the top 10%, which is just a dramatic number. And 40% of the total demand that you have here is the instantaneous creation of cooling. So those are those big machines that we've put in to instantaneously create that load. This is a seven-day chart. Now we're looking chronologically. There's the 28,000 output hour on August 2nd. But the interesting part is 12 hours before or after, you are pretty close to the average load for that grid. So for a very short period of time, it cycles up and cycles back down to meet these very short intermittent loads. This has major impacts on price. So if you take it to, let's look at gasoline. If gasoline was $2.49 a gallon during the day and 99 cents at night, everybody would fill up at nighttime. It would be completely obvious to do that. But if we look at how the utilities have been trying to incentivize everybody for decades, it's the same sort of thing, but they just don't say it that clearly. Utilities, this is a utility, it's got a flat, what they call a flat rate, so that's the same energy cost day and night, 5.4 cents. But they have a demand charge of $15, and a demand charge is charged on a monthly basis. It's for the highest kW draw for any 15-minute period in the entire month. And so if you factor that kW demand charge into anything that has helped setting the peak demand, so that would be things that are running during the day, it turns out that the cost for energy really here on this rate is about 14.5 cents during the day and 5.5 cents at night. So a huge difference between day and night power, but it's really not made very clear to people, or it's certainly not presented to them in this way. So this big use of energy that's been caused by air conditioning has caused daytime power rates to go up pretty dramatically. So if we now look at a building, let's just apply it. If you look at this chart, you've got hours on the x-axis, you've got kW on the y, so the area of the curve is kWh. So you've got a certain amount of energy usage. You've got a peak load of 1,500. The average load is 800. So if we looked at what the load factor for this building is, it's about 53%. That's pretty similar to what that grid is that I showed you earlier. Well, if we now put energy storage on there, we can take all this cooling, so that this 40%, that's the instantaneous creation of cooling. So that's not the moving of the energy around, that's the creation of it by your chillers or your air conditioning system. So if we shift that to the nighttime period, our energy usage doesn't change, and we're going to be talking about modeling in a minute. The peak load gets dropped by 40%. And if you look, and the average load stays the same because it's a kW usage. And so if you do the load factor of this building, it's about 88%. So that's a really high load factor. Well, who gets the best electric rates? Industry. Why? Because their load factors are good. So this is, you can make your commercial building look like an industrial building. You can shape the load depending on when those renewables are available or the cost is low. This is an actual building. This was Consumer Reports, the Consumers Union who makes Consumer Reports. This has storage in it. This is hours of the day across the X. The Y-axis is kW divided by 4, so those are 15-minute demand periods, and then days of the year. So you've got not much usage winter nights, but summer nights you're making a lot of cooling, and that's being used during the day. So this building stays nice in this yellow zone. These red peaks you see here, that actually wasn't failing. This utility had an on-peak period that started at 11 a.m. So this is the chilling equipment dropping off and going on to storage, and now storage is handling all the cooling. If it didn't have storage, all this kWh would be stacked up on these daytime, very expensive hours. So for an ice storage system, you can do it with water storage, chilled water. You can do it with ice storage. I'll just go over the ice storage quickly on how it works. They're all chiller-based systems now, so it's a standard chiller that are used for building. It's a closed, pressurized system. So what are the differences? Well, the storage device I'll describe in a minute. We've got control logic, so the chiller is going to be operating at night instead of just directly during the day to meet the load. You've got heat transfer fluid in there. Storage tanks, they can be round, they can be rectangular, they can be plastic, they can be steel. But the tank is an insulated tank. This one's round. It's got a lot of tubing in it, making up a heat exchanger. The tubing takes up 10% of the volume. The water takes up 80% of the volume. And then when you freeze the tank to ice, the water level expands, so there's an expansion zone on the top. There's no moving parts in the Ice-on-Coil tanks. The only thing moving in and out is the antifreeze going into the tank and coming out of it. At night, you're supplying a 25-degree solution. It goes in the inside of the tubing. You build ice on the tubes. By the end of the night, you have a solid block of ice. It goes into the tank at 25, comes out at 31. That goes on for about 8 hours. This building is designed partial storage, so it's a 1,000-ton peak load. 500-ton chiller is all you need to do the job. During the day, if the load's below 500, the chiller meets the load directly and a temperature modulating valve bypasses it. During the load, when it gets above 500, the chiller does the first part of the load, and then the temperature modulating valve just has some of the cooling come from the tanks to cool the load. It starts melting the ice closest to the heat exchanger, and so you have the ice cooling the solution. So you've shifted a major part of the building's electric load to the storage during the day. Any kind of chillers can do it. The systems that are out there now are getting more modularized. So any storage system needs the chiller, it needs the ice storage tanks, and then it needs everything else. And some manufacturers are putting it together in a package. So it's got the pumps, the controls, the valves, sensors, makeup, everything you need. And so it's getting easier and easier to design these systems. It's more like a unitary system than an applied design. There's lots of energy storage out there, ice storage. These are just half of the installations. These are the ones done by our company. We probably have 4,000 out there. There's another 4,000 with the different manufacturers. So there's a lot of energy storage out there right now, and thermal storage, and way more than installed batteries. So batteries are something that we're going to need because we need to handle the electric loads. But thermal is something that you want to look at first, and I'll go into that in a minute. But there is a lot of it out there. You can see it's concentrated in areas, dense areas. Florida has incentives, Texas has incentives, but out in the Midwest here, there's not a lot of incentives, financial incentives, other than the arbitrage between day and night power. This is Manhattan kind of tipped on its side, and these are installations that have gone in the last 10 years. So we've got a lot of energy storage getting added to the dense urban environments. And if you think about the whole renewable and renewables, we have to collect the energy and store it. And I really see us collecting the energies offshore and in the suburbs. And a lot of the storage is going to be inside the buildings in the dense urban environments. Study was done recently on the levelized cost. So this looks at a 20-year, 30-year lifespan of lithium ion versus thermal. So it's clear indicator that thermal is dramatically less expensive installed than batteries are. ASHRAE TC 6.9 committee has been gathering information lately in the last 3 years on the costs of the different technologies that we see in different reports. And you can see, pumped hydro is very mature, long life. Batteries are relatively mature now. Their life is really not that long if you compare it to a power plant, but they have useful, good cycle efficiencies, right? Whereas pumped hydro is not quite as good there. Flywheels are pretty new, compressed air, that's demo stage. Thermal's very mature, very high cycle efficiencies and very long life. So thermal is something you want to look at first. And finally, I'm going to start looking at the comparison of electric batteries and thermal batteries. And it's not a matter of versus. You have to think of these as we're going to need all types of energy storage to satisfy our energy storage needs and make these renewables dispatchable. And so it's really not chemicals versus, it's chemicals with thermal when you go into buildings. So if you look at just some general costs, these costs are probably out of date, so don't take them to the bank. But if you look at an ice storage system, one tank, you're getting 18 kilowatts of cooling for a 6-hour period. You're kind of in this range per kW or per kWh. For a battery, doing the same amount of kW and kWh, discharging over the 6 hours, it's dramatically higher prices. Now, batteries have a nice ability that they can discharge quickly. And so where we're seeing batteries being used in buildings, they have faster discharges than normally what you're doing with thermal. So I looked at using them over a 3-hour period as opposed to a 6, and the financial numbers get better, but still not dramatically, more expensive than the thermal storage. Well, there's one other thing about thermal, in that when I showed you before that a partial storage system, so let me just describe that there's 2 types of thermal storage systems in buildings. There's full storage, and full storage you make enough stored cooling at night to not run any chiller or any compression during the day. So you need a lot of compressor to make the storage, you need a lot of storage to store it, and you can make the entire load during the day. Then there's partial storage, which was the example I gave before. So on that 1,000-ton building, you can put in a 500 or a 600-ton chiller, run that at night, make the cooling, make the storage. You need much less storage now. Now you run that 500-ton chiller during the day, and you have the storage help that 500-ton chiller meet the 1,000-ton load. So in that partial storage scenario, the money you save on the smaller chiller system can go and pay for some of the storage that you purchased. And when you factor that in, your numbers get dramatically lower for the thermal storage system. Now that can't be done with the batteries. So the battery is an add-on to the system. Well, if now we take a system and we do it individually, we have the thermal storage, you'd have prices like this without partial storage. You have batteries with the 3-hour discharge. But now let's do batteries with ice. So 2/3 the ice, 1/3 battery. Now your installed cost per kW and your kWh numbers are getting very attractive. Well, if we factor in the partial storage into the numbers, this is what the system would look if it was just ice, but let's do the combined system. And now you're looking at numbers, for the installed cost per kWh that Elon Musk would like to be to, in 8 years, right? And we could be there tomorrow if you put in a system that is combining thermal and electrical batteries. So the thing you really want to have as a takeaway is, you want to use thermal batteries to meet thermal loads in buildings, and you want to have electric batteries meet electric loads in buildings. And that is going to end up being the best financial customer solution for your customer. And conversely, it makes zero sense to put an electric battery, just drop that on a building, and have that battery have 40% of that battery's energy go to a compressor that's instantaneously cooling it. Those electrons are way too valuable and way too expensive. You want them to go to something that needs electrons, like a computer screen or a pump or a motor or a fan, but you don't want it to go to a compressor that's instantaneously cooling something. And finally, they asked me to throw in a list of different incentives that are out there. There's a lot of incentive programs out there from the different utilities in the different states incentivizing the use of peak load reduction and energy storage. New York's got historically high prices per kW. It's over $50 a kW, not the $15 I said in my example before. They have some very large rebates. Boston has $40 demand charge. Long Island's got $30 demand charges. All over the country, $14, $15 is pretty standard. But so this is kind of a listing of different areas that have the incentives out there. And, you know, don't take these to the bank. They seem to change on a yearly or monthly basis. So please check with your utility. I threw in the Michigan one. There aren't incentives there, but we've got a lot of installations there. And really, that's always just the sale of the arbitrage between day and night power. And at $25, it's an absolute slam dunk. At $14, it makes a lot of sense. You just have to look at it on an individual basis. And with that, Miles, I think I've kind of given the broad brush on energy storage.
Great, fantastic. Thank you so much, Mark. Super exciting technology. I'm going to go ahead and take control, and then we'll have Carl present. Nina, if you can pass control. And then also just for the listeners, we're going to have, sorry, bear with me here. We'll have questions at the end. You can write questions, and we'll get as many of those answered as we can. Bear with me here. There we go. All right. Should be seeing the screen now. Carl, take it away.
All right. Thanks, Miles. And thank you, Mark, for that very thorough introduction on the whole concept of thermal storage. My name is Carl Heine, and I am I'm a PhD student right now at Colorado School of Mines, but I also have the fortunate opportunity to conduct some research here at ONREL. Today, I'll be talking to you about thermal storage and the modeling side, because I believe that making the modeling of thermal storage accessible is really the key to demonstrating its potential and getting it into installations. So we'll talk about these agenda items in stride. I'll just pause momentarily for the recording. Here we go. So first up is modeling challenges. I use Energy Plus, which is the Department of Energy's physics-based building energy simulation platform. And then Open Studio, that other icon there, is the graphical user interface. And it also has a software development kit backend that we can use for scripting to make it easier, because Energy Plus is essentially a text-based entry, and it can be challenging to make sure things are working properly. And that brings me to my first point, which is ice storage models right now are pretty tedious to build. And the reason for that is just the nature of our simulation software as it stands, and the fact that as soon as you add an ice element, you then have to modify all of your control elements within the model to make the ice charge and discharge properly. Getting the control strategies then is not very obvious. So because we have to manually go in and tweak these different control strategies, it's difficult to explore in a parametric manner different operating conditions that you may want to look at for your particular building. And then it's also somewhat challenging to impose power limits on the chiller hardware within the simulation software. And this is just the nature of building energy simulation. The idea is you calculate the loads and then you determine how much electricity your chiller is going to require to meet that load. And what we can do in real life is limit how much power that chiller will use, which is sort of the inverse of what your building energy simulation software will give you. So those first two bullets are really what I spend most of my time on. The third bullet is that the performance data that we have for ice tanks is good, but it's generic. And there's ongoing work, some lab testing with different devices to characterize different performance curves for different manufacturers' hardware. But like I said, I focus on the first two. My goal is to improve these models and really improve the accessibility of these models. So what I want to do and have been working on is take the basic, if you were to start with the ASHRAE design guide for cool thermal storage, the latest edition of that was published in January of this year. But if you open that up and you look up ice storage, it'll list out a bunch of different configuration options, various storage objectives. We talked about full storage and partial storage beforehand. You can also have a chiller priority or a storage priority when you're discharging the ice. And all of these sorts of options are available within the design guide. But to actually implement those in your models, if you want to explore the potential of storage for your building, becomes tedious. So what I do is I write scripting methods to implement these in various models. Some of the potential benefits that we can then explore once we have a ice storage model is we can explore chiller downsizing effects. Obviously, you can get potential reduced capital costs from downsizing your chiller. You can also improve your efficiencies by operating at higher average part loads when you are operating the chiller, and with your day-night operating schemes, operating the chiller at high load at night, you can get very good coefficients of performance, so better efficiencies at night than you would have during the day. And surprisingly, when you combine those two, you can actually end up having a reduction in your annual electricity use because you're using a smaller device and you're using it at a higher efficiency point, even though you're putting energy into and out of storage. So you've made up for your losses in the round trip efficiency. Other benefits of thermal storage is that it is very effective at shifting your cooling load out of the off-peak hours, and it is a controllable energy storage. So Mark mentioned all these incentives seem to change every year. Well, with an active thermal storage system, you can adjust your control schemes as necessary to match future changes in the electricity rate structures. So just to have some example results, I ran two sets of examples, or I will be presenting two sets of examples for today. The first one is a centralized plant. We use the DOE prototype building models. This one was modeled with an air-cooled chiller down in Houston, so we could get some good winter cooling loads. The example looks, you can see on the right-hand side of the screen a sketch of the, or a schematic rather, of the supply side. So we have a single chiller, and then we have an ice tank added there, and those little green arrows are control objects, how we actuate turning the ice on and off. We took this model straight from the DOE prototype and applied the measure with a few clicks, and 30 seconds later we had the ice added to our model, our building model, with these high-level control strategy set and hardware configuration set. And by doing so, we could then perform energy simulations. The first plot here of results that I'm showing is just an average September day for that particular model, just the weekdays. In the dashed line, you have the baseline energy use throughout the day, 24 hours across the x-axis. And then in the green, you have the with ice storage. And we're basically seeing energy simulation results for a building model that reflect what Mark was talking about earlier with the improvement in load coverage or load factor. What is also very important when we talk electricity rates is how much can we reduce our maximum demand charge. So this plot shows the baseline in gray, the red is our with ice storage, and then the percentage values on top of the red indicate the reduction in total KW, or excuse me, maximum KW for that month. And they range from 12 to 23% throughout the entire year. A summary of the results for this model, we were able to achieve a 4% reduction in total energy use, again, because we've downsized the chiller and we've increased our efficiency. You can see a 17% average monthly reduction in our demand, our peak demand. Our COP goes up by 20%, and our annual electricity for the chiller goes down by about 20%. We also included tracked runtime hours we observed that we're running at slightly less, but about the same time. And the key to note is between these two models is we have no change in the unmet hours for the building. So our model is still achieving what it needs to achieve in terms of meeting the cooling load of the building. Distributed ice storage I want to mention, because this is another option for smaller scale, where you don't have a big central chiller plant. Instead, you have a bunch of RTUs. So these devices are called unitary thermal storage systems. The ones on the market range from 20 to 40 ton-hours. The 20-ton-hours are typically marketed for residential, 40-ton-hours for commercial. They work with 3 to 20-ton AC units, and they're designed to shift between 4 and 6 hours of cooling load. One thing that it does do to your system is it adds a cooling coil to the airstream, so you have additional fan pressure drop as it crosses that coil. However, these are, you could think of them like plug and play, where you plug them into where you already have an existing RTU, or where perhaps you would retrofit an RTU, so you get the storage right there as you plug into the airstream. Some example results for this. In this case, we used the DOE prototype retail building. And for this, we did a climate zone sweep. So we modeled this building with the various ASHRAE 90.1 standards across 15 climate zones. And we added the ice batteries to each RTU. And then we applied 2 different utility rates to observe the financial performance. We also did some energy analysis, but it's easier to just look at the dollar amounts at the end to observe the potential benefit. The 2 utility rates we used, the dashed line is a rate that uses a lower demand charge but a higher time of use multiplier, and the solid black line is the inverse of that. When we ran the simulations, took our energy results and then applied the calculations using those utility rates, we achieved annual savings in total electricity bill between 6 to 12%, with outliers being in San Francisco and Fairbanks, Alaska, unsurprisingly. But we were able to achieve, because of our energy savings during the middle of the day with that 5-hour full storage or that 6-hour full storage, we were able to achieve significant energy savings. And in this particular model, we did not downsize the RTUs. So that is also another potential area of savings as you look at it.
Carl, that's based on total energy?
Yeah, total building energy. Yep. Thanks. So just in summary, what I'd like to leave you with today is that we are working on making the energy modeling accessible so that we can easily employ and explore different ice storage configurations and controls, so that we can quantify the potential benefits for any user who may be looking at an upgrade in their HVAC system. And then also realize that these options don't only exist for the large central plants, but you can also find systems to get ice in a distributed sense. And with that, that concludes my presentation. So I'll turn it back over to Miles.
Thank you, Carl. That's fantastic. A lot of exciting stuff going on. Thermal storage. I think that our partners will be thrilled for this information. I think that was super interesting. So thank you again. I think what we're going to do here, let's see what we have left for time, 15 minutes. I believe we should be able to gather some questions online. Michael, are you able to see the questions? Okay. While we're doing that, if there are questions that come up, bear with me. I'm just trying to make sure I can see them if anybody's writing. Maybe I'll just talk to this last sort of closing slide, some of our thoughts and ideas looking ahead with the space conditioning tech team. First being a thermal energy storage landscaping study, sort of in the works right now, but we're just kind of looking for feedback and interest as we move forward with the next upcoming year. Also, another ongoing conversation has been around building automation systems for small commercial applications and looking at grid interactive efficient buildings, so GEB buildings, and just finding opportunities to work with our partners around that. I don't know, Michael, if you want to speak to any of these points, feel free to jump in.
I do want to mention one thing, new research that's ongoing now that is being conducted and will it will be coming out in the next year or two. But at ONREL, we are looking with Department of Energy projects on looking at the combination of battery and thermal energy storage, and trying to understand that, what are the best combinations there. As Mark was saying, it really makes sense to start to look at that, especially as we get more and more renewables either on the grid or on your building. And what is that optimal combination of thermal and also looking at not only cold storage but hot thermal storage too. Does that make sense? And then potentially even dehumidification or latent thermal storage is also an option that we're looking at. And so as we move forward, we need to consider all these storage options, and we're trying to understand that the best performance and from an energy and cost point of view.
And with the dehumidification, you're referring to like a liquid desiccant?
Right.
Okay. Great. Okay, I still am not able to see any questions. Let's see.
So this is Mark. I've got one which I think is fascinating. I was very happy to see the modeling, and it's showing the energy reduction that you can get because of fully loading the equipment up. If you look at ASHRAE performance of chillers, they show full load performance and then they show part load performance, but those part loads are not at the same temperature. They assume, let's say a chiller is running at 50%. In the testing and the reporting of it, they reduce the condenser temperature, the cooling tower temperature, pretty dramatically, and the corresponding very high efficiency that you get is not necessarily at the temperature at the full load. So what the simulation has done, and one of the reasons you're seeing this better performance, is when you put in an oversized system on design day, it is operating at the very high temperatures, but it's operating at part load. And also, for instance, in the off seasons, in the January and February on that chart that was shown, you saw very high efficiencies. Well, that's because you're not turning the chiller on. You're running the chiller for a couple hours to fully charge up the tanks, and then you won't run it for weeks, and all you'll be running is a pump. So there's a lot of efficiency gains keeping a chiller not going from 0 to 20% at that really part load condition. So I thought that was fascinating results.
Yeah, thanks, Mark. I think that's the power of building energy simulation, because we can capture that so much better than we might if we were just simply looking over a daily load profile and crunching numbers in Excel. We're getting those simultaneous effects
Exactly.
in our calculations.
Exactly.
Great. I don't know if Nina is able to read any questions that are coming in. I'm not seeing any pop up on my question board, so I just want to make sure we're not leaving people in the dark here. I'll continue on here. Another sort of outreach request. There's an ongoing RFI for a field study, looking for field study participants, and this is sort of the last call to get involved with this. I apologize, we can't really speak to it in greater detail, but if you have any questions or if you're interested in getting involved and you're not already a partner, feel free to contact me, Miles Hayes at onrel.gov there. But it's a joint RFI between GSA Proving Grounds and the Department of Energy High Impact Technology Catalyst Program, and looking for existing active Better Buildings members who would like to participate in a field study that's focused on demand management and building load flexibility. So grid interactive technologies. There's sort of a lot more detail I'd like to provide surrounding this topic, but again, we're looking for a September 6th date. That's the cutoff date for completing a sort of online building profile application. But if you're interested in receiving that, reach out to me and I can get you lined up with the necessary people. Something popped up here. All right, bear with me here. I'm going to try and see if I can find any comments or questions that may be rolling in. All right, I found some questions rolling in. So we've got one question from Joseph. Has NREL looked at the combination of solar to reduce demand percentage and impact downsized TES? Example, K-12 elementary building and schedule aligns with solar day. Mark, I might pass that over to you. I know that you guys have got a lot of thermal storage in K-12 applications. The question was, has NREL looked at the combination of solar to reduce demand percentage? So I guess that's maybe more directed at us, but Mark has got a number of solar installations that have been completed in K-12 elementary schools. Michael, what?
So I'm not aware of any projects we looked at demand with just solar. Solar by itself doesn't usually decrease demand. You have to have some kind of storage or very active load management. And usually that active load management, you end up curtailing services that you don't really want to curtail, but you really need to have that storage to decrease your demand with the solar. Otherwise, it usually doesn't line up.
You have
very
to
well.
You have to remember that demand is any 15-minute period in the entire month. And the logic behind demand is utility had to install this capacity ahead of time so that you could have it. And so if you put just solar on the roof of a school, well, yeah, on most sunny days, that's going to take care of a lot of the demand. But on that cloudy day, it is not. Or when that cloud comes over on a hot day and a thunderstorm comes up, there's still a lot of cooling going on, so you're still setting a high peak. So yeah, as Mike said, you've got to have energy storage or curtail comfort to pupils.
Thanks, Mark. We had another question come in here from Lucas, asking some of the O&M issues or issues to consider with thermal energy storage. Mark, if you want to sort of speak to some of your
Sure. So as I mentioned, there's no moving parts in the main thermal storage technologies that are out there now, right? And it's been around a long time, so the manufacturers know how to make the product and make it so it's going to last. So As far as maintenance, there's almost none on the storage device itself. You're checking the water levels once a year, and in all environments except super dry desert, there is no evaporation of the water. It just stays there. You're checking the glycol concentration in an ice storage system once a year. Manufacturers will do that for free. And you know, it's mainly a controls thing. You're watching, make sure things haven't changed in the controls, but there's no added maintenance, or almost zero added maintenance. And actually the chiller system is usually smaller, so your maintenance costs are usually less because it's based on capacity.
Next question.
Okay, thanks, Mark. I think the last question that came through, with regards to the overall weight of thermal storage systems, do you have any idea, Mark, as to sort of an average weight per square foot when talking about adding on thermal storage?
Well, so the storage tanks can be located, well, I shouldn't say that. In the small systems, you mentioned the Ice Bear, Ice Energy system. Those are normally put on the roof, and so there are weight considerations. I think for the tanks that we manufacture, I think the highest is like 300 pounds per square foot is the weight of the tank. What we have found is that in buildings that are multi-story, meaning 6 floors and up, that the column strength is plenty strong in the buildings, and so all you have to do is distribute the load over to the columns. We've put our tanks on the roof of buildings all over the world. We did one in New York City recently. It's on the 28th floor of a 70-year-old building. So, but that's the general range. You can go to the manufacturer's websites to get actual pounds per square foot on the different products. Ice is less than water storage is because we store a lot more. We store about 10 times the energy and with the same amount of water, so it's a lot less.
And Mark, just to add on to that, you mentioned, or to answer the question on those rooftop units, those Ice Bears, those are approximately 150 pounds per square foot filled.
Well, I think we're just about out of time here. Any other closing comments you want to make, you guys?
No.
Okay, Mark, anything else on your end that you'd like to throw in here?
No, I'm good. Thank you for the opportunity to speak to the group. And if you have any questions, you can find my email online. It's mm@calmac.com.
Absolutely. And thank you for taking the time again, Mark. Really appreciate it. And Carl as well. For the rest of the callers on the phone, again, any feedback, feel free to contact me, the email address on the screen there, or you probably have Michael's contact as well. And we'll be happy to be in touch. Okay. All right. Thank you guys so much. Have a good day.
Thank you.
Bye.